Welcome. We are continuing our discussion of finding areas, still using horizontal strips. Another place where using horizontal strips is convenient is if the region is given in terms of equations in which x is written as a function of y. Like in this example, we have the equations x equals y squared plus 2 and x equals 6. Of course, you can also do this by just switching x and y. Switching x and y just flips the graph, which means the area doesn't change. So the answer would be same as the area bounded by y equals x squared plus 2 and y equals 6. I will leave it to you to work that out and verify you get the same answer. If I set this up using horizontal strips, of course I have to first draw the graph to see which is on left, which is on right. I also have to see where they intersect. Let's first find the points of intersection, or at least their y coordinates. So we set the two equations equal to each other, y squared plus 2 equals 6, and then solve for y. Subtract 2 and then take square root, so y is 2 or negative 2. So y goes from negative 2 to 2. We don't really need x coordinates for this part, but it's easy to see that they have to be 6 because one of the equations is x equals 6. I will record that because it's an alternate way of doing this, which I will discuss at the end, for which we need to know the x coordinates. Now, I need to know which is on left, which is on right, which I can see from the picture, but what if I don't have the picture? If I don't have the picture, since they intersect at only 2 points, we know that one is completely to the left of the other within that interval. You just pick some test value in that interval. I can just pick 0 and compare the two x values when y is 0. If y is 0, in the first equation, x equals y squared plus 2, x comes out to be 2. In the second equation, x comes out to be 6. 6 is bigger than 2. So x equals 6 is further to the right than x equals y squared plus 2 in the interval where y runs from negative 2 to 2. So when I set up the area integral, of course y goes from negative 2 to 2, I have to subtract the smaller from the larger. So I have to subtract y squared plus 2 from 6. Another way to verify is that if you simplify this, the integrand 4 minus y squared will be positive between negative 2 and 2. Y is 0, 4 minus y squared is 4, which is positive. So that verifies that we did in fact subtract in the correct order. Now I just have to do the integration against just the power rule. And antiderivative is 4y minus y cubed over 3. Take the net change from negative 2 to 2, so substitute 2 and negative 2 and subtract, which simplifies to 32 over 3. We could have also done it differently. I could have done one of two things. I could have used symmetry. The area of this whole region is twice the area from the x-axis to the top of the parabola. So I can set up this integral using vertical strips as we used to do before and then double it. Or you can see that this is the area with x going from 2 to 6 and vertical strips running from bottom half of the parabola to the top half. Of course, I have to figure out the equations of the bottom and top halves in the form y equals something in x. I have to solve for y from the equation x equals y squared plus 2. So I subtract 2 from both sides and take the square roots. So y is the positive or negative square root of x minus 2. I'm writing the square root using fractional exponents, so I can do the antiderivative. The top half will be the positive square root, bottom half will be the negative square root. So if I set up the area using vertical strips, x runs from 2 to 6. The top is x minus 2 to the power 1 half. The bottom is negative of x minus 2 to the power 1 half. And then you find the antiderivative. Using a substitution u equals x minus 2. Finish the calculations, you should get 32 over 3.